Welcome back to the Deep Dive. Today, we have a really specific and I think a highly strategic mission for you.
Hmm.
We are taking on the one engineering challenge that, more than any other, seems to differentiate the champions from, well, the also-rans in Formula Student Electric.
I think that's fair to say.
Our task is to develop a comprehensive, truly top-tier engineering requirement specification for the battery management system, the BMS.
And, we have to be clear right from the start. We are not just talking about a checklist to tick off for safety scrutineering.
No.
We're framing this whole deep dive from the perspective of, let's say, an experienced global automotive strategy consultant.
Right.
For a newly formed FSE team, the BMS has to be viewed as the absolute nervous center of the entire electric powertrain. It is the core competitive asset, period.
Exactly. Our sources, and this is coming from, decades of experience across FSG, FSAE, JSAE, they all stress the same thing. The most common mistake is viewing the BMS as solely a regulatory hurdle you have to jump over.
It's a limiting belief, a huge one.
So our mission today is to guide a new team in building a BMS that is, well, inherently a competitive advantage. And we're going to use that rigorous McKinsey-style MECE framework.
Mutually exclusive, collectively exhaustive.
Exactly, to make sure we define requirements that don't just comply, but actually lead the field.
In the hyper-competitive world of Formula Student, the margin between first and fifth place can be just a handful of seconds. It's razor thin. And that difference, it often boils down to how the BMS enables the car to precisely, and I mean precisely, extract every single joule of energy while keeping the whole system balanced right on the edge of its physical limits.
So what we're defining today is really the blueprint.
It's the blueprint for a world-class championship-winning design.
Okay, so let's unpack this strategic vision first, this idea of moving from defense to offense. The consultant report is highly critical of what it calls the compliance-only mindset.
It is.
It calls it the single most common limiting belief. So if a team's only aim is to pass scrutineering, what's the fundamental competitive failure they're making right out of the gate?
They're leaving performance on the table. So much performance.
Just leaving it dead.
At defensive BMS, it focuses on these hard statics thresholds. It's binary. If voltage drops below 3.0 volts, trip the main SDC and shut down the entire car.
Which is safe.
It's safe, yes, but it's incredibly conservative. The entire strategic goal of a championship-level BMS is conquest. It's achieved through extreme energy utilization and data-driven decisions that push the car to the absolute limit of what cells can deliver without, catastrophe.
So what does that strategic shift actually look like in practice? How does a competitive BMS manage power limits dynamically instead of just statically?
Well, it requires integrating real-time internal resistance modeling. So we're talking about using the DC internal resistance, the DCIR of the cells. And that changes dramatically with temperature and state of charge. You combine that with something called power prediction or state of power SOP. The BMS isn't waiting for a problem to happen. It's actively predicting one.
Can you walk us through that prediction? How does that work in the heat of a race?
Certainly. So the BMS master unit, the AMU, it's running this continuous calculation. It's constantly asking, if the driver demands 100 kilowatts right now, given the cell's current temperature is, say, 45 degrees Celsius, and its state of charge is low, maybe 15%.
Right at the end of the race.
Exactly.
Okay.
The instantaneous voltage drop due to internal resistance polarization will push the terminal voltage below our 2.9 volt hard limit in the next 100 milliseconds.
Okay.
So instead of just letting that happen and triggering the hard shutdown, the BMS uses that SOP algorithm to immediately calculate the safe dynamic current limit, the DCL. Maybe that's 80 kilowatts.
And it sends that new lower limit to the VCU.
It transmits this limit in real time to the vehicle control unit via the CAN bus.
So the VCU sees the limit and just automatically reduces the inverter's torque request. The driver might not even feel it, but the car avoids a DNF.
Exactly right. It's a soft control strategy replacing a hard fail. This lets the driver maximize their power output for the whole event while the BMS automatically, gracefully walks that physical limit.
It transforms the BMS from just a passive monitor into an active performance optimizer.
That's the perfect way to put it.
That makes complete sense. Now, let's talk about the data strategy, because the source insists the BMS must function as the vehicle's black box. The strategic target here is sampling critical data at greater than 100 hertz. The benchmark is only 10 hertz. That's a huge engineering requirement, a tenfold increase. Why is that non-negotiable?
It's non-negotiable because of transient events. It all comes down to transients.
Okay.
In a dynamic racing environment, especially when the driver is, aggressively modulating the throttle, these rapid current demands cause transient voltage dips. They're caused by polarization and internal resistance, and these events can happen in milliseconds.
Way faster than your sampling rate if you're only at 10 hertz.
If your sampling frequency is only 10 hertz, you're sampling every 100 milliseconds. You are absolutely guaranteed to miss the microspikes that cause these false alarms.
And a false alarm is, well, it's an immediate season failure in many cases.
Precisely. A high frequency rate, 100 hertz, means sampling every 10 milliseconds. It captures those spikes accurately. This allows the SOP algorithm to filter out the transient noise from genuine safety threats, preventing those unnecessary season-ending shutdowns.
But the value goes beyond just preventing a DNF, right? This data is critical for the design event.
It is, and that's the second component of the whole black box strategy, the engineering argument.
So why does high-frequency data logging win over the judges?
Because the design event judges are evaluating your engineering process and your argument. It's not just about the final product. So if you stand there and claim you've designed a cooling system that works efficiently, you have to prove it. If you claim your computational fluid dynamics, your CFD model, predicted an even thermal gradient across the module, you need the data to validate that simulation.
So the high-frequency data, with 100% cell coverage on temperature and voltage, that provides the forensic evidence.
Exactly. Without that black box recording, your claims are just theory. The data validates your engineering mastery. It proves you did the work.
That's a really powerful point. Okay, let's drill down into the key performance indicators, the KPIs, that define this world-class design. We've moved past simple compliance. Now we're defining the performance ceiling. Let's start with mass reduction. The benchmark is 2 kilograms, but the strategic target is below 1.5 kilos, and that includes the harnesses. Is that target even achievable without making some pretty significant compromises?
It's extremely aggressive, but it's absolutely necessary. In FSE, mass is performance. It's as simple as that.
Every gram counts.
Every single gram you save on the BMS is a direct improvement in the car's dynamic response, its braking capability, and it maximizes that all-important efficiency score in the endurance event.
So to hit that sub 1.5 kilogram target, you have to be ruthless. You
have to be ruthless. Using a modular architecture, which we'll get into, optimizing your PCB layer count, minimizing every millimeter of wiring loom length. A 500-gram saving on the BMS, which is positioned low and centrally, is worth so much more than 500 grams somewhere else in the car.
Okay, next up. Precision. The voltage measurement precision target is aiming for ±1 millivolt across the full operating temp range. That's compared to a benchmark of ±2 millivolts. Having the error. Why is that so critical?
This precision target is, you could argue, the highest stakes KPI in the entire system.
Wow.
Because it directly determines your achievable depth of discharge of your DOD in the endurance race. Well, the state of charge, the SOC, it's derived primarily from the open circuit voltage curve of the cell. And that OCV curve is extremely flat in the middle of the charge range, but it becomes very, very steep at the end of discharge.
Meaning a tiny error in your voltage measurement leads to a massive uncertainty in the remaining SOC, right when you need that accuracy the most.
Precisely. If your voltage measurement error is ±2 millivolts, your resulting SOC uncertainty might be 5% when the pack is nearly empty.
So to be safe, your driver has to stop or back off way early.
Your driver has to significantly reduce power when the BMS thinks it has 10% SOC remaining, because they risk hitting that hard shutdown limit at 3.0 V purely due to measurement uncertainty.
You're leaving 10% of your energy on the track.
Exactly. Now, if you achieve ±1 millivolt precision, your uncertainty drops dramatically, often to below 1%.
And that allows you to hit that strategic target SOC error of less than 1% using the advanced algorithms we'll talk about.
Correct. With an SOC error under 1%, the team knows they can run the battery down to 1% of the total available energy without risking that catastrophic undervoltage shutdown.
And that small shift, from stopping at 10% remaining to stopping at 1%.
That is the difference between winning and losing the endurance event. It translates directly to using 99% of your available energy, maximizing your runtime and your score.
It's a competitive advantage earned by high-quality components and very precise calibration. And finally, the reliability KPI. Mean time between failures greater than 500 hours and 0 false positives. That zero false positive target seems, well, almost impossible in such a complex, vibrating system.
It represents the operational reality of FSC. It's a competition of elimination, first and foremost.
Right.
If your BMS triggers a single unnecessary shutdown due to a voltage spike, some noise, a faulty connector, you get a DNF, and your entire season's effort is just wiped out.
So to achieve that, the design has to incorporate multiple layers of redundancy.
Redundancy, which we'll detail, and it has to rely heavily on those advanced algorithms we talked about, like filtering and SOP, to distinguish genuine physical faults from transient noise artifacts. Reliability is the foundation. All performance rests on it.
Okay, we've established the performance goals. Now we have to turn to the non-negotiable boundary conditions, the FS rules. Our sources really highlight that recent rule changes have fundamentally dictated changes in hardware architecture, especially around thermal monitoring.
Yeah, the rules are not static. They evolve constantly to improve safety based on real-world incidents, and this forces teams to continuously innovate. The big paradigm shift is centered on the latest revisions to rules like FSG EV 5.8, which addresses cell temperature monitoring with unprecedented specificity.
Let's focus on that mandate then. Temperature sensors, the NTC thermistors, must maintain direct physical contact with the cell's negative terminal. Why the severity in specifying that exact contact point?
This is all based on thermal physics and, frankly, historical safety lapses. For the common cylindrical cells, your 18650s, your 21700s, the outer metal can is typically connected to the negative terminal, and that can is the primary heat conduction path, especially under rapid discharge.
So older, non-compliant designs might have just put a sensor nearby.
Exactly. They might place a sensor simply near the bus bar or even glue it to the plastic insulation. These methods give you a delayed or inaccurate reading. They effectively mask localized thermal hotspots that can precede a thermal runaway event.
So the rule closes that safety loophole.
It does.
I see the safety rationale, but what are the immediate, practical design implications for an engineering team? This sounds like it completely kills the simplest, cheapest way of designing cell monitoring PCBs.
It absolutely does. This mandate is the death knell for simple, rigid PCBs that are just placed near the terminals. A rigid PCB cannot guarantee consistent, tight physical contact across maybe 100 or more cells, especially when the pack is thermally cycling and vibrating aggressively during a race.
So a competitive, compliant design has to adopt.
You're forced into either flexible PCBs, flex PCBs, or semi-flexible rigid flex solutions, or you have to go with these elaborate, custom, spring-loaded sensing probes.
Wait, if a new team has to adopt flex PCBs, that immediately adds a lot of complexity and cost to their manufacturing supply chain.
It does.
We're talking specialized suppliers, higher material costs, longer lead times.
Precisely. And this is where that strategic planning comes in. The flex PCB route, while it is more costly and complex, is the most robust solution for both compliance and reliability. It allows the monitoring circuit to contour precisely around the cell terminals, maintaining that required direct contact. It's a non-negotiable element of a world-class system.
And what about coverage? The rules mandate monitoring a minimum of 30% of the cells, but the strategic advice is for 100% coverage. Why take on the manufacturing overhead of monitoring every single cell?
Because compliance is 30%, but competition requires 100%. If you only measure 30% of the cells, you're creating blind spots. You might miss the single outlier cell in the geometric center of a module that, due to poor airflow or just manufacturing variance, is running 5 degrees Celsius hotter than its neighbors.
And if you miss that one hot cell, your entire engineering argument about your cooling system efficiency just falls apart in the design event.
Exactly. Full coverage lets the team capture the precise thermal gradient across the entire module. This data is absolutely vital for validating your complex CFD simulations. It moves your design event justification from "we think it works" to "we proved it works with real-time data from every single cell."
Let's pivot to the safety circuit in the SDC. The BMS is the judge here. How does a competitive design ensure functional safety beyond just simple software logic?
Functional safety demands non-programmable logic redundancy. So the BMS master unit, the AMU, has to have the physical ability to open the SDC via a fail-safe mechanism, usually a normally open relay or a solid-state switch.
But the critical layer is what happens when the software crashes.
Because all software crashes eventually.
Yeah, right. So that's the external hardware watchdog.
Yes. Top teams incorporate hardware watchdogs and analog comparators that are designed for a high automotive safety integrity level, or ASIL. You can think of the watchdog as a physical tripwire. The main microcontroller, the MCU, has to periodically send a feed the dog pulse to this external, independent piece of hardware.
And if it doesn't?
If the MCU freezes due to a memory overflow, a power spike, a bad line of code, and fails to feed the watchdog within a very tight tolerance, say 100 milliseconds, then the external circuit, which runs entirely on robust, non-programmable logic, must physically force the SDC open in less than 500 milliseconds.
So that's the difference between relying on the potentially corrupted brain of the car and relying on a simple, dedicated circuit breaker.
It's the very essence of ASIL compliance. You need hardware-enforced redundancy for catastrophic failure modes. You have to ensure that even if the software fails spectacularly, the high-voltage system remains safely disconnected.
Now, let's address that critical design trap you mentioned, the brake system plausibility device, the BSPD, and its interaction with the BMS. A lot of new teams try to cut corners here. What's the non-compliant path they take?
The temptation is to use the digital current data that the BMS is already calculating and just transmit it to the BSPD over the CAN bus.
Okay.
The BSPD is rule mandated to prevent the driver from simultaneously applying full throttle and full brake. To judge that plausibility, it needs to know the instantaneous power draw.
But using CAN data is non-compliant because the BSPD has to be a non-programmable safety device.
Exactly. The rules are very clear. The BSPD must receive a raw, physically isolated analog signal directly from the current sensor. The data has to be verifiable, immediate, and completely immune to software tampering or a CAN bus failure.
So this immediately impacts the current sensor choice. It mandates what you call heterogeneous redundancy. How does a team achieve that?
The sensor strategy has to support a dual output. You need one output for the BMS master unit. This will be a high-precision digital output, probably CAN or SPI, and it's used for those crucial SOC and SOP calculations.
Right.
And you need a second, separate, physically isolated analog output from the same measurement apparatus dedicated solely to feeding the BSPD. Heterogeneous redundancy just means using two different signal paths, digital versus analog, from the same physical measurement to satisfy two different safety requirements. This sensor choice has to be locked in very early in the design cycle. So having defined the performance and regulatory demands, we have to choose the topology that meets them while optimizing for weight and noise immunity. This is where FSAE analysis of the architectures is just vital.
Okay, let's start by quickly dismissing the non-competitive architectures. First, the centralized BMS. Why is this a guaranteed route to mediocrity in modern FSE?
A centralized architecture is defined by having one single large PCB that connects directly to every single cell in the pack. Now, it has two attractive qualities: low PCB cost and simpler software logic.
But the disadvantages are?
They are competitively catastrophic.
Let's start with the harness weight.
It's a massive harness weight. For a typical 144 cell pack, you're running at least 144 individual voltage sense wires, plus all the thermal wires, the entire length of the accumulator box. We're talking maybe 1.5 to 2 meters.
Wow.
We estimate a pure centralized harness easily weighs 10 to 15 kilograms. It's just unacceptable.
And worse.
Worse, those hundreds of meters of wire act as antenna, which leads to catastrophic noise immunity issues, especially near the high-power inverter. Any serious team has to avoid this topology.
Okay, then you have the really revolutionary approach, wireless BMS or WBMS. It completely solves the harness problem. So why is it currently just for R&D and not the competitive standard?
Well, the zero harness weight and the simplest assembly are incredibly compelling, but the technology just isn't robust enough yet for high-stakes competition.
The main concern is reliability.
It's communication reliability and latency. You have extremely high electromagnetic interference, EMI, generated by the main drive inverter, a massive noise source right next to these tiny, low-power wireless nodes.
So you can't guarantee the signal gets through.
Can you guarantee that critical fault data will be transmitted instantly with low latency when the system is under peak EMI stress? I don't think so. Plus, power harvesting or managing individual power sources for each node just adds more complexity. It's a great future technology, but it's too risky for a team trying to win tomorrow.
Which leaves us with the distributed or modular architecture. Our sources identify this as the recommended golden standard, practiced by established winners like AMZ Racing and TU Delft. What makes it the optimal choice?
The distributed architecture is really the elegant compromise. It involves placing these small cell monitoring units, CMUs or satellite boards, directly on each module, say a 12-cell module.
And the advantages are immediate.
Immediate, dramatically reduced harness weight, down to maybe 2 or 3 kilograms total, and vastly superior voltage sampling accuracy because the measurement is taken milliseconds away from the cell terminal. It's scalable, it's reliable, and it's very noise immune.
So let's detail the recommended version of this. Distributed isoSPI, what are the specific functional requirements for the two main components?
So the brain is the master unit, the accumulator management unit, or AMU. It has to reside in the protected low voltage section of the car.
Right.
Its computational responsibilities are all high level, running the complex state of charge, the EKF and state of power, the SOP algorithms. It also manages the external CAN-FD communication with the VCU and provides the physical control interface for the accumulator isolation relays and the pre-charge circuit.
And the physical requirements for the slave units, the CMUs?
The CMUs are the workhorses. They're simple, lightweight boards, and each one operates at the high potential of its respective module. Their mandate is purely localized and physical, highly accurate cell voltage and temperature sampling, and managing the passive balancing for just that module. They're essentially data acquisition satellites.
The internal communication protocol is key here, isoSPI or isolated SPI. Why is this so much better than trying to use a conventional bus system between the modules?
isoSPI, which uses chips like the LTC6820 or LTC6813, is just superior for these high-voltage communication chains. First, it uses simple, robust, twisted pair wiring, which is highly resistant to common mode noise. That's crucial when you're linking nodes across massive voltage potentials.
And it's efficient.
Highly efficient at transmitting large quantities of raw cell data voltages, temperatures, faults at up to 1 megabit per second.
And critically, it simplifies the slave design, right?
Yes. Running CAN to every node would require expensive CAN transceivers, microcontrollers, crystal oscillators on every single CMU. isoSPI eliminates all of that. It dramatically simplifies the slave board, which reduces size, weight, power consumption, and the thermal complexity right at the cell level.
Since these CMUs are operating at high potential, isolation is critical. What are the engineering requirements for the pulse transformers used to isolate the communications?
Safety margin is everything here. The isolation barrier, which is provided by those pulse transformers, must have a voltage margin that is significantly greater than the maximum system voltage.
What's the rule of thumb?
The strategic requirement is for a minimum 2 times margin. So if you are running a 600-volt system, you must specify isolation components rated for greater than 1200 volts. This ensures physical separation and safety, especially under fault conditions.
Let's finish this section with external communication, AMU to VCU. We already established that traditional CAN 2.0 is basically obsolete for a competitive system. Why is CAN-FD flexible data rate so essential?
The data density requirement is the killer for CAN 2.0. I mean, if we're sampling 144 cell voltages at our strategic target of over 100 hertz, plus all the temperature, current, and fault data, the sheer volume of real-time telemetry is massive.
Which just can't handle it.
Traditional CAN 2.0, limited to 500 kilobits per second and a tiny 8-byte payload, it simply cannot handle this load without dangerously high bus utilization, and that leads to latency and potential data loss.
And the moment you lose real-time data, your sophisticated SOP algorithm can no longer issue dynamic limits, which forces the system back to those conservative hard cutoffs.
Exactly. CAN-FD solves this. It increases the speed up to 5 megabits per second, and crucially, it expands the payload size to 64 bytes. This massively increases the available bandwidth. It guarantees that critical real-time safety and performance information, like those dynamic power limits and fault statuses, are relayed to the VCU instantly. Safety and performance are maintained simultaneously, without any latency.
Okay, now we move into the physical components, where the rubber really meets the road. The analog front end, the AFE chip, sets the absolute physical ceiling for the entire BMS performance. And we have the two main competitors, Analog Devices and Texas Instruments.
Yes, the ADI LTC6813-1 versus the TI BQ79616-Q1. Choosing between these is a classic engineering trade-off between, let's say, integration efficiency and functional safety score.
Let's start with integration efficiency. The LTC6814-1 offers 18 channels per chip, while the TI offers 16. That channel difference seems minor, but for a 144 series system, that affects the bill of materials pretty significantly.
It affects complexity, weight, and cost directly. For a 144 cell pack, the 18-channel LTC6813 requires only 8 chips in the stack.
Okay.
The 16-channel BQ7961 Steed requires 9. One fewer chip means less PCB space, lower component count, less power consumption, and reduced complexity in debugging. That integration advantage is actually substantial for weight optimization.
But the trade-off is safety certification. The TI chip is ASIL-D compliant, the highest standard, while the ADI is ASIL-2 capable.
Yeah.
Why does this matter so much in the competitive context of FSE?
ASIL-D compliance, which is backed by really comprehensive documentation and internal redundancy features within the chip itself, is a massive scoring plus in the design event. It demonstrates to the judges that the team has prioritized functional safety validation to the highest automotive standard. While the LTC is highly robust and Cell 2 capable, the TI part provides a better engineering argument on paper regarding inherent safety design.
And regarding communication, we already said we liked isoSPI.
The LTC 6813 is designed around that robust isoSPI protocol, which is mature and has extensive community support. The TI chip uses a proprietary differential UART architecture. Now, it's accurate, but it's a newer design, and it represents a slightly higher supply chain and debug risk for a new team that's still learning the ropes.
So synthesizing all that for a new competitive team, what's the final decision rationale?
For a new team, the LTC 6813- represents the lower-risk, highly integrated choice. The 18 channels simplify the mechanical and electrical stack design, and the isoSPI is a proven, battle-tested communications backbone.
So the one chip saving and the maturity of the platform.
It outweighs the slight scoring advantage you might gain from the ASIL-D badge of the TI chip, which might introduce unforeseen debugging headaches.
Okay, that's a clear recommendation. Moving on to balancing. Active versus passive. The report just dismisses active balancing entirely. I have to push back on that a little, though. For electric vehicles generally, active balancing is far more efficient. It transfers energy instead of just burning it off. Why are we telling a competitive team to use the less efficient method?
That is a great question, and it speaks directly to the unique constraints of Formula Student. Active balancing is superior for long-term cell life and maximum efficiency over thousands of charge cycles, like in a passenger car. But in FSE, the endurance event is only 30 minutes long. The energy you gain by transferring charge, which is usually less than 1% of the total capacity, it just does not justify the competitive penalty.
And that penalty is?
Weight and complexity. Active balancing requires these large, heavy inductors, transformers, and complex switching circuitry. You're adding 2 to 3 kilograms and introducing a huge number of potential failure points. In a short race, that weight penalty immediately outweighs the negligible energy you recover. Simple, lightweight, and reliable passive balancing is the strategic winner here.
So if we choose passive balancing, how do we ensure it's powerful enough to be effective and, fast?
The specification has to require a high balancing current. Standard AFE chips, they only support maybe 50 to 100 milliamps internally, which is far too slow for the fast competition turnarounds.
So you need more power.
This strategic requirement is designing an external high-power MOSFETs and external power resistors to support a current greater than 300 milliamps.
Okay, let's quantify that thermal consequence, though. If we're balancing aggressively at 300 milliamps at 4.2 volts, that's 1.26 watts per cell dissipated as heat.
It is.
That's a huge thermal load, especially when you multiply it across 144 cells.
It's a critical design requirement. This heat cannot be ignored. The PCB design has to be thermally coupled to the module's cooling system. This mandates the use of massive copper pores on the monitoring boards to draw that heat away from the resistors and into the cooling plate or the airflow path.
And if the team fails to design for that specific heat load,
their balancing system will overheat, it'll throttle down, and it'll become ineffective. And that results in an uneven state of charge during the next charging cycle.
Okay, next, current sensing. Accuracy here determines the long-term integrity of our SOC estimation. Hall effect versus smart shunt. What's the definitive argument for the smart shunt?
The definitive argument is precision and stability. Hall effect sensors are appealing because they're non-contact and they offer good isolation, but they suffer from these intrinsic physics problems.
Such as
high temperature drift, zero-point drift, and hysteresis, especially at low current draw. They are simply not accurate enough to maintain that required SOC precision of less than 1%.
And the smart shunt, like the Isabel and Hit IVTS series, solves these issues.
It uses the fundamental law of physics Ohm's law to measure the voltage drop across a highly precise, known shunt resistance. Modern smart shunts integrate high-resolution ADCs and temperature compensation, and they achieve incredible precision, often down to 0.1% accuracy.
And they output clean data.
Crucially, yes. They output calibrated, aggregated data current, voltage, and amp hours directly via a digital bus. They are the standard for high-performance OEMs precisely because of this reliable precision.
So the smart shunt is the primary choice, but we still need that backup analog signal for the BSPD.
Correct. So the strategic decision is this. Your primary measurement is the smart shunt for performance data. Your secondary redundant measurement is a low-cost Hall sensor used only to provide the required raw, physically isolated analog signal to the BSPD. That satisfies the heterogeneous redundancy rule without compromising the precision of your main SoC loop.
Okay, finally for hardware, let's detail the precharge circuit. This prevents that catastrophic inrush current. What are the engineering specifics?
The precharge sequence has to prevent damage to the AR contacts and the inverter's massive DC link capacitors. The requirement is strict. The precharge must charge the DC link voltage to 95% of the battery voltage in less than 2 seconds.
This sounds like a straightforward RC time constant calculation, but I'm guessing the component selection is key.
It is. The resistor has to be carefully sized based on the total DC link capacitance and the required time constant. But furthermore, that resistor has to be a high pulse power component because it must absorb all the stored energy calculated by E equals 1/2 CV squared in that short pulse duration.
And if it fails?
If the precharge fails to reach 95% in 5 seconds, the system has to abort the startup sequence and trigger a safety alarm, preventing the ARs from closing under dangerous conditions.
And the discharge circuit for when the STC opens.
The function of the discharge circuit is to safely reduce the high voltage remaining on the DC link capacitors to below the touch-safe voltage of 60 volts in less than 5 seconds. This is typically implemented with a normally closed relay that switches in a high-power resistor, dissipating that energy safely. And that circuit has to be strategically located to comply with all of the tractive system accumulator container rules, usually near the main disconnects.
All right, so we've built the best possible hardware ceiling. Now we turn to the software, which transforms all this raw data into performance and safety. This is where the competitive differentiation really happens, right?
Absolutely. The hardware dictates what you can do, but the software determines what you will do. And the first critical challenge is state of charge estimation. We have to completely abandon simple amp-hour integration or Coulomb counting.
Why does Coulomb counting fail so reliably under racing conditions?
Because it's an open-loop system. It's like driving from New York to California blindfolded, relying solely on your odometer.
Hookles. Okay.
Any small error, the current sensor's initial offset, temperature drift, noise, even a slightly mistyped cell capacity, it just accumulates over time. It leads to this massive, uncorrectable drift. In a 30-minute race, the error can easily be 5 to 10%.
Which forces the team to maintain a huge safety buffer and costs them the race.
Exactly.
So the sophisticated solution is the extended Kalman filter, or EKF. Now, this is complex mathematics. Can you simplify the principle of how the EKF keeps the SoC so accurate?
I can try. The EKF is a recursive self-correcting estimator. Crucially, it treats the battery as a dynamic electrochemical system, not just a dumb charge bucket.
Okay.
We use a second-order 7-in equivalent circuit model to represent the cell, which incorporates not only the main internal resistance, R0, but also 2 different time constants that represent the polarization effects.
The polarization voltage. That's the voltage drop that happens after the initial instantaneous drop, right?
Correct. And that polarization voltage is extremely difficult to track accurately, but it's crucial for determining the true available capacity and the real-time voltage response.
So how does the EKF handle it?
The EKF operates in a loop. First, the system predicts the next SoC and voltage based on the current being drawn. That's the predict step. Second, it compares the predicted voltage to the actual ultra-precise voltage measured by the AFE chip. That's the correct step.
And the difference between the two is the error.
Yes, the measurement error. And that is used to constantly adjust the internal state parameters and correct the SoC prediction.
So it's constantly correcting its internal mathematical model against real-world measurements, which prevents the open-loop drift of Coulomb counting.
Exactly. This is how we achieve that strategic target of less than 1% SoC error, even under aggressive current fluctuation, which is vital for racing. And a well-implemented EKF allows us to estimate parameters we can't measure directly, like the internal polarization voltage and R0, which are then fed into our power prediction algorithms.
Okay, I have to ask the critical question based on the sources. The EKF requires serious computational horsepower. The ambition of this algorithm is actually dictating the hardware budget for the master unit MCU. Why is that?
Because the EKF involves continuous matrix operations, specifically updating the covariance matrices and the Kalman gain. These calculations are computationally intensive and they require floating point arithmetic.
So you can't run this on a cheap chip.
You cannot run a high-speed EKF on a basic 8-bit or 16-bit integer-based MCU. This dictates the selection of a powerful, floating-point-enabled microcontroller, typically an ARM Cortex-M4F or increasingly an M7 chip, just to perform the necessary matrix algebra in real time at a frequency that supports that 100 Hz sampling rate.
That's a very clear link between software ambition and physical cost. Okay, next up, the state of power algorithm, SOP, which we know is crucial for preventing a DNF. This is where we define the dynamic current limits, the DCL.
SOP is the proactive safety intelligence. It is constantly predicting the immediate future. Its function is to calculate the maximum available discharge power and regenerative power for a look-ahead time, typically about 10 seconds.
How does it do that?
It uses the precise inputs from the EKF, the current SOC, the temperature of the hottest cell, and the estimated internal resistance. And it runs a short-term simulation to determine the power limit that will prevent the cell voltage from crossing the hard limits within that 10-second window.
So it's not waiting for the voltage to drop. It calculates the maximum current the cell can safely deliver right now.
Correct. And this DCL is transmitted instantly via CAN FD to the inverter. If the driver demands 100 kilowatts, but the DCL is 80 kilowatts, the VCU respects the 80 kilowatt limit and linearly ramps down the available torque.
Which results in a smooth, strategic power reduction that the driver can manage, instead of that terrifying sudden DNF shutdown.
It keeps the car on the track. It maximizes competitive distance.
Finally, let's talk about the development process. For a new team, developing a system this complex must involve some rigorous process control. The recommendation is model-based design, or MBD. Why is adopting tools like MATLAB Simulink so critical, even with a limited budget?
MBD is the modern standard because it drastically accelerates development and it minimizes errors. Instead of writing raw C code and then debugging it in the car, which is slow and very dangerous, MBD allows the team to develop and verify all the control algorithms, including the ECUSF and SOP, graphically within environments like Simulink.
And the core benefit is verification before you even have the physical assembly.
The ability to automatically generate verified embedded C code using tools like Embedded Coder is a massive time saver. But more importantly, MBD enables rigorous verification using hardware-in-the-loop simulation, HIL.
So you can test it on a simulator.
You can use battery emulators, simulating all 144 cells, their voltages, their internal resistance, and connect them to the actual master BMU. This lets the team test all the complex logic, the edge cases, the fault injection scenarios.
Like simulating a broken wire or an overcharge.
Exactly, or a sudden temperature spike. You do it all in a safe, virtual environment weeks or months before the physical hardware is integrated. This dramatically reduces costly and dangerous field debugging time. So the BMS is intrinsically linked to the physical integrity of the accumulator. If the mechanical and thermal design is flawed, no algorithm in the world can save you.
Let's revisit that controversial thermal management strategy then. The strategic recommendation for a new team is optimized air cooling, despite the fact that champion teams often use these highly sophisticated liquid systems. Are we telling a new team to just ignore the best in the world, or is this a calculated risk based solely on the weight constraint?
It's a calculated strategic trade-off. While liquid cooling does offer superior maximum performance, it imposes a crippling weight and complexity penalty on a new team. We're talking 3 to 5 kilograms for the pump, the radiator, the pipes, and the fluid.
And that added weight demands a huge engineering effort in structural integrity.
And it introduces critical failure modes like leaks.
So the path to making air cooling competitive requires a specific, intelligent choice in cell selection.
Absolutely. Optimized air cooling is only viable if the team selects extremely high performance, low internal resistance cells, something like the Molicel P45B, with an IR well below 7 milliamps.
Because they generate less heat to begin with.
These cells inherently generate far less heat under load, which dramatically reduces the thermal management burden. The team's focus then shifts to using CFD to optimize the air ducts, ensuring uniform flow across all the modules and eliminating any localized hotspots.
And the DMS master unit controls this system for maximum efficiency.
Yes. The BMS has to function as the intelligent controller. It manages fan speed via pulse width modulation, PWM, based on the input data. Specifically, it should only ramp up cooling power based on the highest individual cell temperature, Tmax. This maximizes energy efficiency and conserves the precious low-voltage power supply.
Moving to mechanical integration, the racing environment is basically a constant earthquake. We need robust components. What are the key strategies for vibration resistance?
The BMS has to be designed to withstand standards, like FSAE J2380. This requires securing all large components, for instance, large capacitors, inductors, even harness connectors. They have to be stabilized by potting or securing them with high-temperature RTV silicone.
To prevent them from just vibrating loose.
It prevents them from fatiguing their leads or vibrating loose over the course of the dynamic events.
And what about environmental protection? We have carbon fiber dust, moisture, potential debris everywhere.
All PCBs, especially those sensitive CMU satellites, must be protected with conformal coating, often called 3-proof paint. This thin layer prevents electrical shorts caused by conductive carbon fiber dust or moisture ingress.
And connectors.
Critically, connections must be automotive grade. We have to avoid simple pin headers or flimsy consumer connectors. We mandate locking high-retention connectors like the Molex Mini 50 or JST JWPF series to resist the high-frequency vibrations that cause connection failures.
Reliability hinges on predicting failure. Let's dedicate some time to the failure modes and effects analysis, the FMEA, which is central to getting a high score in the design event safety section. Walk us through the detail of the required mitigations for a few key modes.
The FMEA demonstrates that you've thought through the catastrophic risks and provided layers of defense.
Okay, take example mode 1, an open wire in a cell voltage sense line.
If a wire breaks, the AFE might read a floating value or 0, which could potentially cause the BMS to mistakenly try to overcharge that cell. The mitigation has to be immediate. The AFE chip itself, using an internal current pull-down source, must detect the open circuit. This detection must instantaneously trigger the SDC shutdown logic, bypassing the main control loop. It has to be a hardware-driven fault detection.
Example mode 2, a balancing MOSFET short circuits. This is a terrifying failure, a continuous, uncontrolled discharge leading to thermal runaway.
The mitigation here requires both software vigilance and a hardware backup. The software layer has to constantly monitor for abnormal voltage drops on that cell, even when balancing is officially disabled.
And the hardware layer.
The hardware layer provides the physical safety brake, a self-resetting fuse, a PTC, placed in series with the balancing resistor. If the MOSFET shorts and draws excessive current, the PTC heats up, it opens the circuit, and it physically mitigates the risk before the cell is catastrophically damaged.
And example mode 3, the ultimate black swan. The main microcontroller unit freezes.
If the MCU freezes, the entire system is paralyzed. It can't react to any new or existing faults, and it leaves the SDC closed. The mitigation is that external hardware watchdog we detailed earlier. This non-programmable logic exists solely to monitor the MCU's health signal. If that signal is missed for a predetermined short time, the external hardware must bypass the frozen MCU entirely and physically cut the SDC power. This is the final layer of defense, proving true functional safety independence.
This detailed FMEA needs equally detailed testing. What's the single most important component of the validation plan for a new team?
It is the rigorous use of hardware-in-the-loop testing, HIL testing. I cannot stress this enough. Teams must use battery emulators, high-fidelity simulators, to test every single line of DMS logic, especially the EKF and SOP algorithms, and every single one of those failure modes by injecting simulated faults. HIL testing saves money, it reduces danger, and it's the only way to fully verify that your complex software logic correctly triggers the hardware shutdown mechanisms every single time.
And outside of the HL simulator?
Rigorous environmental testing is mandatory for long-term reliability. The PCBs have to undergo thermal cycling from -20 degrees C up to +80 degrees C to ensure that the voltage sampling accuracy remains within that ±1 millivolt target across the full operating range, and that communication links remain stable. And vibration bench testing must also confirm that our chosen automotive connectors and component potting strategies can actually withstand the track punishment. So, We have completed the full requirements specification for a truly competitive champion-level BMS to synthesize the three core strategic choices. Adopt the distributed isoSPI architecture for its optimal blend of low weight and noise immunity.
Right.
Select the LTC 6813-1's the analog front end for its high integration efficiency and proven stability.
Okay.
And commit to the extended Kalman filter (EKF) algorithm to achieve the sub 1% SoC accuracy you need to use 99% of your energy.
This brings us to the final strategic recommendation for a new team, the make versus buy decision. The consultant report strongly advocates for self-development, for the team to make its own BMS. As you mentioned, robust off-the-shelf units like Orion exist. Why is this strategic decision so non-negotiable for a competitive FS team?
Purchasing a commercial BMS is a performance ceiling. It's as simple as that. Off-the-shelf units are often heavy, they're bulky, and most critically, they are black boxes.
Right.
They give you a generic safety profile but zero access to the deep competitive algorithm optimization, the EKF that provides 1% accuracy, or the SOP that dynamically prevents a DNF.
So self-development is the only way to demonstrate that core engineering competence to the design event judges.
And it is the only way to tailor your control limits precisely to the electrochemical characteristics of your specific battery cells. If you want to win, you must own the intelligence layer. You have to make the BMS.
So this statement of requirements is the technical map to a champion-level powertrain. We've defined the optimal structure, the key components, and the mathematical brain necessary for victory.
And just remember, the BMS has to move beyond being a reactive safety guard. It must be a proactive information provider, constantly feeding intelligence to the driver and the VCU.
And that leads perfectly to our final provocative thought for you to consider. We briefly touched on the insulation monitoring device, the IMD, which is critical during the rain test, and its use of a complex PWM signal to communicate its status to the BMS master unit.
Right.
Now, compliance requires the BMU to simply trigger the SDC if the IMD detects resistance below 500 ohms per volt.
It's a hard cutoff, and it's there to prevent electrocution risk.
But strategically, how can the master BMU process the IMD's raw, complex PWM output, which contains detailed isolation resistance data, to inform the driver or the autonomous system about the incipient risk of electrical leakage long before the system is forced to shut down? Utilizing that complex PWM data stream proactively, maybe by displaying an isolation resistance trend on the dashboard, transforms the IMD from a last-second safety switch into a crucial piece of strategic, real-time diagnostic information. That proactive knowledge, allowing the team to anticipate and plan around the limits of the rain test, is the ultimate expression of the BMS as a strategic asset.